This is a short video to get you guys to start thinking about what a regression analysis is going to be and how we use it in econometrics. So what I did is I downloaded some very small portion of a data set from the census on state and local tax revenue. And the data is shown in the upper left here that I copied from Excel, but I did add this variable here that I'm just calling time. And since I only went back to the first quarter of 2019, I basically have 5 quarters, and I gave them the increment of 1, 2, 3, 4, 5. So what I plotted over here in the plot is just the seasonally adjusted total tax revenue as compared to time. And notice this is not a good practice. Normally your minimum on the y-axis would be 0 or it would be marked, but this was just an automatic plot that came out of Excel to get us started. So what we're thinking about is each of these blue dots is the actual data. And what we're going to be searching for or learning how to find is the line of best fit. So let's just think about for a moment what is the best fit. So each of these data points, we could think about the line that was fit to the data was essentially done like this. This is what is the expected value of Y tax revenue given that we're in time period 1 or first quarter. This one is on the line, so this is the expected value of Y. This would be the expected tax revenue given that we're in time period 2, and so on. So when we worked on those conditional probability distribution functions, we worked on that to directly connect it to this idea that we want to know what would be the best guess for Y given what's going on with X. So why is that the best guess? Well, what we're thinking about is each of these differences from actual data to the line are some error terms. That one's very close. So each UI is an error term. So the slope and the y-intercept of this line that's of best fit, the place that it comes from is a function that had minimized adding up all the error terms, squaring them so they don't cancel each other out, summing them, and by minimizing that function with respect to choosing a y-intercept, which we're going to call beta 0, and choosing a slope, which is beta 1. So by adjusting the y-intercept and the slope so that this is as small as possible is where that line is coming from. So to just demonstrate it briefly, we can think about what if it was the same slope but a different intercept, like a little bit scooted up? Well, if we calculated the sum of the squared error terms, the distance from the actual data to that line, took each of them, squared them, and added it up, it would be larger than the line that we have. Or alternatively, if we thought about, well, what if it's the same y-intercept but a different slope? So maybe it starts around the same, here's where our y-intercept would be. What if it, well, I better use a different color. What if it started there but was a little bit flatter? Well, if we used that line, did the same thing, found each error term, squared it, and added it up, it would be larger value than the one that we have. So these parameters are chosen or optimized to minimize that sum squared error term function. So by minimizing that function, we get particular formulas to find the slope and find the y-intercept. And I will show you those formulas in a later video, but this is just to introduce you to the idea conceptually of how this line of best fit is connected to the conditional probability of y given what the value of x is in our story.